video, we're going to talk about symmetry. We're going to talk about asymptotes, both vertical and horizontal asymptotes. And we're also going to talk about end behavior. Now, in the graphical sense, the word symmetry in mathematics carries essentially the same meaning as it does in art. The picture, in this case the graph, looks the same when viewed in more than one way. The interesting thing about mathematical symmetry is that it can be characterized numerically and algebraically as well. We'll be looking at three particular types of symmetry, each of which can be spotted easily from a graph, a table of values, or an algebraic formula once you know what to look for. Since it's the connections among the three models, graphical, numerical, and algebraic, that we need to emphasize in this section, we will illustrate the various symmetries in all three ways, side by side. Now, another way you can talk about symmetry is if you have a way to fold one part of the graph onto the other. That will also be symmetric. The only one you really have to worry about is when you're symmetric to the origin. We'll get into that. Now, symmetry with respect to the y-axis. These will be the even functions. Our example that we have here is f of x equals x squared. So graphically, you know that x squared is a parabola. It's a quadratic that opens up, and you know that it's going to have the y-axis as its line of symmetry. Numerically, you can look at the table from -3 to 3. You can see that all the numbers match. -3, 9, and 3, 9 are both on the graph. For all x in the domain of f of -x equals f of x. This is something we're going to be using very much. Make sure you pay attention to that. That's how we're going to decide if functions are even, odd, or neither. We're going to put -x into our function. Now, symmetry with respect to the x-axis. Now, these ones are not functions. Our example here is x equals y squared, or plus or minus the square root of x. These won't be functions because they don't pass the vertical line test, but we can say that x negative y is on the graph whenever x, y is on the graph. So again, here 9, -3 is on the graph, also 9, 3 is on the graph. Now, the ones we're really worried about here are symmetry with respect to the origin. These are our odd functions. So f of x equals x third is our example. Well, you can see that if x, y is on the graph, then -x, -y is also on the graph. That's how that one works. So again, we have f of -x equals -f of x. That will tell us it's an odd function. So in summary, if f of -x equals f of x, this will be an even function. If f of -x equals a negative f of x, this will be an odd function. Algebraically, that's all we're really going to be worried about in this section. Moving on to example 9. State whether the function is even, odd, or neither. Support graphically, confirm algebraically. So here we go. We're going to support this graph. We're going to graph it first. So here's our graph. You can see here that it does look like an even function. The way we decide, we're going to put -x in for all of our x's. Well, when you square a negative number, you're going to get a positive number. So this just says then that f of -x equals f of x. And from our summary before, because if f of -x equals f of x, that tells me it's even. This one here will be an even function. Now if we look at B, judging here, it It doesn't look like it's symmetric to the x-axis. It doesn't look like it's symmetric to the y-axis. It doesn't look like it's symmetric to the origin, but algebraically we'll still look at it. F of negative x equals a negative x squared minus 2 times a negative x minus 2. Well, that means f of negative x will equal x squared plus 2x minus 2. In order for this to be an even function, this needs to be exactly the same as this. So f of negative x does not equal f of x or negative f of x. So this one will be neither. It's neither even nor odd. In our next one here, we have x to the third divided by 4 minus x squared. Interesting. Almost looks like it might be an odd function. Let's check that out algebraically. So h of negative x will equal a negative x cubed over 4 minus a negative x squared. Simplifying this, we'll get a negative x cubed up top and 4 minus x squared on the bottom. So that means h of negative x will equal a negative x cubed over 4 minus x squared, which does equal a negative h of x. So because h of negative x equals a negative h of x, this tells me it is an odd function. Next, we're moving on to asymptotes. Consider the graph of the function f of x equals 2x squared divided by 4 minus x squared. The graph appears to flatten out to the right and to the left, getting closer and closer to the horizontal line y equals negative 2. We would call this line a horizontal asymptote. Similarly, the graph appears to flatten out as it goes off the top and bottom of the screen, getting closer and closer to the vertical lines x equals negative 2 and x equals positive 2. We call these lines vertical asymptotes. If we superimpose the asymptotes onto the figure as dashed lines, you can see that they kind of form a template that describes the limiting behavior of the graph. Really what you're doing, if you think about it, you want to take, to find that horizontal asymptote, you want to divide your leading terms. So in the top, my leading term is 2x squared. In the denominator, my leading term is negative x squared. 2x squared divided by negative x squared is negative 2. That's how you get your horizontal asymptote of y equals negative 2. Now to get your vertical asymptotes, remember the denominator cannot equal 0. So if you factor that, you get 4 plus x and 4 minus, 2 plus x and 2 minus x. That's where we get our negative 2 and 2. Now since asymptotes describe the behavior of the graph at its horizontal and vertical extremities, the definition of asymptote can best be stated with the limit notation. I'm going to be a stickler on this. We need to learn how to work with limit notation, especially if you plan on moving on to calculus. In this definition, note that x arrow a negative means x approaches a from the left, while x approaches a plus means as x approaches a from the right. So you got to be able to read your graph from left to the right. Now, we have a formal definition of an asymptote here. The line y equals b is a horizontal asymptote of the graph of a function f of x if f of x approaches a limit of b as x approaches positive or negative infinity. In limit notation, the limit of the function, so the limit of f of x as x approaches negative infinity, will equal b, or the limit of the function, limit of f of x as x approaches positive infinity, will equal b. Now, the line x equals a is a vertical asymptote of the graph of a function if f of x approaches a limit of positive or negative infinity as x approaches a from either direction. So in limit notation, and we'll go through this again, the limit of f of x as x approaches a from the left side is equal to positive or negative infinity, and the limit of f of x as x approaches a from the right side will be positive or negative infinity. This definition is kind of confusing if you're not used to it, so it might take you a couple times to understand it, or you can ask questions during class. Now, example 10. Use a method of your choice to find all horizontal and vertical asymptotes of the function. Now, the way we're going to do this, we're going to use algebraic methods here. Now, to find our vertical asymptotes, work on those first. I know x squared minus x minus 2 cannot equal 0. So what I'm going to do, I'm going to factor the left side. And this will be x, and 2 and 1. It's got to be a negative 2 and a positive 1. This cannot equal 0. That means x minus 2 cannot equal 0. X plus 1 cannot equal 0. Which tells me then x cannot equal 2, and x cannot equal negative 1. So my vertical asymptotes, x equals 2, x equals negative 1. These are my vertical asymptotes. Now, for notation's sake, you'll see me a lot of times just putting VA and HA for horizontal asymptotes. Now, you heard me say before, to find the horizontal asymptotes, we want to take the leading term in the numerator divided by the leading term in the denominator. So it'd be y equals x over x squared, which would be 1 over x. Now, what we need to do here, if we want 1 over x, you need to think about it like this. Let's pretend x is 1. 1 divided by 1, you get 1. How about x is 10? You get 0.1. Or how about 100? You get 0.01. Or 1,000. What do you notice as x gets bigger and bigger? The number's getting smaller and smaller. And when we see 1e to the negative 4th, that really means 10, or 1 times 10 to the negative 4th, which is really close to 0. So my horizontal asymptote will be y is equal to 0. This will be your horizontal asymptote. Moving on to B. Again, vertical asymptote here. X squared minus 1 cannot equal 0, which means x plus 1 times x minus 1 cannot equal 0, which means x cannot equal positive or negative 1. That means my vertical asymptote, x equal 1, x equal negative 1. There's your vertical asymptotes. Now to find your horizontal asymptote, y equals x squared divided by x squared. That means y will equal 1 will be your horizontal asymptote. Now if we're to graph this, it's actually fairly simple. X squared plus 2 divided by x squared minus 1. And you can see there, we'll have a horizontal asymptote. We'll have a horizontal asymptote at y equals 1. Right about there. Then we'll have two vertical asymptotes. We'll have one here and right next to it. There's the two vertical asymptotes. Simple enough to graph it and find out. It's a lot easier to figure out vertical asymptotes and horizontal asymptotes actually algebraically though. Moving on to end behavior. A horizontal asymptote gives one kind of end behavior for a function because it shows how the function behaves as it goes up toward either end of the x-axis. Not all graphs approach lines, but it is helpful to consider what does happen out there. We illustrate with a few examples. So look at example 11. Match the function with the corresponding graph by considering end behavior and asymptotes. All graphs are shown in the same viewing window. Well, let's look at A. Horizontal asymptote will be 3x over x squared. So y will equal 3 over x. That means my horizontal asymptote be y equals 0. Which of these has a horizontal asymptote of y equals 0? Well, it looks like this one does. There's A. Now for B, my horizontal asymptote, 3x squared over x squared.
I'll see you on Monday.
Y will equal 3 will be my horizontal asymptote. Which one of these has a y equals 3 as a horizontal asymptote? Well, there's my horizontal asymptote there. So there's B. Now for C, it's not so much going to be a horizontal asymptote. Let's do this. Y equals 3x cubed over x squared, which means y will equal 3x. That's really going to be a slant asymptote. That means this one here will be y equals 3x. This will be C. Here is the line y equals 3x. Which should make it nice and easy for D, but let's do the horizontal asymptote anyway. 3x to the fourth divided by x squared, that will actually equal 3x squared, which is simply a parabola. There's your end behavior asymptote, and here is D. Now we'll go through more of the limit notation as we get in deeper into this section and into the chapter. But it's a nice, easy way to remember end behavior. It's not always going to be a horizontal line for an asymptote. It could be a parabola. It could be to the third power. Really doesn't matter. It all depends on what the degree of your numerator and the degree of your denominator are. Again, if you should have any questions, you need to let me know immediately so I can get to you and answer your questions as quickly as possible.